A magnitude 7.8 earthquake struck off the coast of southern Mindanao on June 8, 2026, and within moments entire sections of the Philippine coastline were no longer where they had been the day before. Along the shores of Sarangani and neighbouring coastal communities, residents emerged after the violent shaking to confront a landscape that seemed unfamiliar. Areas that had always been underwater were suddenly exposed to the air. Coral reefs stretched across the horizon as broad rocky plains. Boats that once floated close to shore found themselves separated from the sea by newly emerged ground. Lagoons appeared drained. Tidal channels looked transformed. The coastline itself had shifted outward. This was not the temporary retreat of water associated with a tsunami. It was not an unusually low tide. It was not a seasonal change in sea level. The land had risen. The earthquake centered southwest of Cablalan and west of Maasim in the waters off southern Mindanao, released energy accumulated over centuries within one of the most active tectonic regions on Earth. Deep beneath the sea, immense sections of the crust moved abruptly against one another. In a matter of seconds, geological forces that normally operate across thousands or even millions of years accomplished a transformation visible to the naked eye. The event measured magnitude 7.8 and originated at a depth of approximately 34 miles, or about 55 kilometers. The shaking spread across a vast region of the southern Philippines and was felt far beyond Mindanao. Buildings swayed, roads cracked, power systems failed, and communities throughout the region experienced intense ground motion. Yet, among all the consequences of the earthquake, one effect captured extraordinary attention. The coastline itself had changed. To understand why this happened, it is necessary to examine the geological framework that created the earthquake in the first place. The southern Philippines occupies one of the most tectonically complicated regions anywhere on the planet. Here, multiple plates and smaller crustal blocks interact in a constantly evolving network of faults, trenches, folds, and volcanic arcs. Unlike regions situated within the stable interiors of continents, Mindanao exists at the boundary between powerful geological systems that remain in continual motion. These motions occur slowly on a human timescale. Year after year, the crust moves only a few inches or a few centimeters. Yet, over decades, centuries, and millennia, those seemingly insignificant movements accumulate enormous stress. Southwestern Mindanao lies near one of the most important features in this tectonic environment, the Cotabato Trench. Far offshore, hidden beneath the waters of the Celebes Sea, the trench marks a location where oceanic lithosphere descends into Earth's interior. This process, known as subduction, is among the most powerful geological mechanisms on the planet. As one plate descends beneath another, stress accumulates along the interface, separating them. Rocks become compressed. Crustal blocks bend and deform. Entire sections of the Earth's outer shell are forced into positions they would not naturally occupy. For years, decades, or even centuries, these rocks may remain locked together despite the continuing motion of the plates. The strain builds silently. Then, when the accumulated stress exceeds the strength of the rocks, the system fails. The result is an earthquake. In the case of the June earthquake, seismic analyses indicate that the movement was dominated by thrust faulting. This distinction is critical because it explains why the earthquake produced such remarkable uplift along the coast. Not all earthquakes move the ground in the same manner. Some earthquakes involve horizontal motion, where blocks of crust slide past one another. Others involve extension, where the crust is pulled apart. Still others involve compression, where one block is forced upward relative to another. The June earthquake belonged primarily to this final category. The seismic mechanism showed characteristics associated with reverse or thrust faulting. Measurements of the rupture indicated motion consistent with a powerful compressional event. One section of the crust was driven upward relative to another. In practical terms, the geological structure behaved like an enormous wedge. As movement occurred deep underground, the overriding block was pushed upward. That uplift propagated toward the surface. The result was visible not only on land, but across the coastal seabed itself. Large sections of reef and shallow marine environments rose together with the coastline. The process is known as coseismic uplift. The word coseismic simply means that the deformation occurred during the earthquake itself. Rather than taking years or centuries, the change happened in seconds. One moment the reefs were submerged. The next moment they were exposed. One moment the shoreline occupied a familiar position. The next moment it had shifted dramatically seaward. Reports emerging from affected communities described stretches of newly exposed reef extending approximately 200 meters, or roughly 656 feet, beyond the former shoreline. That figure attracted considerable attention because it provided a tangible demonstration of the scale of the deformation. A vertical uplift of only a few feet, or about 1 meter, can translate into a surprisingly large horizontal displacement in shallow coastal settings. Imagine a gently sloping seabed extending offshore. If that entire surface rises several feet, or around 1 meter, vast areas that were previously underwater may emerge above sea level. This is exactly what appears to have happened in portions of southern Mindanao. The newly exposed reef flats became some of the most striking visual evidence of the earthquake's power. Corals that had spent decades growing beneath the water suddenly found themselves exposed to sunlight and air. Marine organisms adapted to submerged conditions faced immediate environmental stress. Pools became isolated, channels changed shape. Ecological relationships developed over generations were altered almost instantly. For scientists, these exposed reefs provide an extraordinary record of tectonic movement. For local communities, they represent a permanent transformation of familiar landscapes. One of the most important aspects of this phenomenon is that it is not temporary. Following large earthquakes, people often wonder whether the land will eventually return to its previous position. In most cases involving major thrust fault earthquakes, the answer is no. The uplift becomes part of the landscape. The crust does not simply settle back into place. This principle is closely connected to a concept known as elastic rebound. For years before an earthquake, rocks deform as tectonic stress accumulates. They bend and store energy, much like a compressed spring. When rupture finally occurs, part of that stored energy is released, allowing the rocks to move into a new configuration. Although the deformation process involves elastic behavior, the earthquake itself produces permanent displacement. The rocks break, the fault slips, the crust assumes a new position. That new position becomes the starting point for future tectonic evolution. This explains why ancient uplifted coral terraces can be found throughout many tectonically active regions around the world. Each terrace records a previous episode of uplift. Each raised reef represents an ancient shoreline left stranded above sea level by an earthquake or long-term tectonic movement. The coastlines of southern Mindanao may now preserve a fresh example of this process. Future generations could potentially observe these newly elevated reefs as geological markers of the 2026 earthquake. The significance of the Cotabato Trench in this event cannot be overstated. Although the trench receives less international attention than some of the world's more famous subduction zones, its history reveals extraordinary seismic potential. The feature developed through the interaction of tectonic systems operating along the southwestern margin of the Philippine Mobile Belt. Over millions of years, subduction shaped the regional landscape, created volcanic arcs, deformed sedimentary basins, and generated powerful earthquakes. Historical records demonstrate that the region is capable of producing some of the largest earthquakes in Philippine history. Among the most notable was the devastating Moro Gulf earthquake of 1976. That event reached approximately magnitude 8 and generated a destructive tsunami that caused widespread loss of life across coastal communities. Even earlier, another major earthquake struck the region during the early 20th century. These events serve as reminders that the tectonic forces operating beneath Mindanao remain active. The June earthquake joins that historical sequence as one of the most significant seismic events to affect the Philippines in recent decades. Measurements indicate that convergence within parts of the Cotabato system proceeds at rates approaching several inches per year, or several centimeters per year. While that pace may appear insignificant, geological time transforms such movements into immense accumulations of strain. Each year adds a little more stress. Each decade adds more. Eventually, the system reaches a breaking point. The June rupture represented one such release. Yet Uplift was only part of the story. Earthquakes rarely produce uniform deformation across an entire region. When one area rises, another may sink. This pattern results from the geometry of fault movement and the redistribution of stress throughout the crust. As reports emerged from southern Mindanao, observations began indicating that some locations experienced the opposite effect. Instead of uplift, portions of the landscape appeared to undergo subsidence. In certain coastal zones, residents reported changes in water levels that suggested the land had dropped relative to the sea. Elsewhere, newly formed depressions appeared in the ground. Particularly notable were reports from Balut Island and several coastal areas where sinkholes emerged in the days following the earthquake. These features generated understandable concern. Large openings appearing suddenly within the ground naturally raise questions about stability and future hazards. While detailed investigations continue, the occurrence of sinkholes following a major earthquake is not unprecedented. Strong shaking can destabilize subsurface materials, especially where limestone formations, cavities, fractures or groundwater systems already exist. The earthquake acts as a trigger. Hidden weaknesses become visible. Existing voids may collapse. Previously stable ground may fail. The result can be the abrupt appearance of sinkholes ranging from small depressions to substantial openings. Their presence highlights an important reality about major earthquakes. The shaking itself is only one aspect of the event. The landscape continues responding long after the main rupture ends. In the days after the earthquake, aftershocks rippled through the region with relentless persistence. Hundreds were recorded, including several large enough to be strongly felt across southern Mindanao. Each aftershock served as a reminder that the crust was still adjusting to the enormous redistribution of stress caused by the main rupture. For communities already coping with damaged homes and altered coastlines, these repeated tremors created an atmosphere of uncertainty. Cracks widened. Unstable slopes shifted further. Structures weakened by the initial earthquake faced additional strain. In places where the land had already been fractured, every new shock raised concerns about further ground failure. Yet, from a geological perspective, the aftershock sequence represented a normal consequence of a fault system seeking a new state of equilibrium. The earthquake had not simply broken a single point beneath the earth. Instead, an extensive section of crust had moved. The surrounding rocks now needed to accommodate that movement. As they adjusted, smaller faults slipped, fractures propagated, and stress migrated through neighbouring sections of the crust. This process continues after virtually every major earthquake. What made the Mindanao event especially remarkable was the scale of visible surface change accompanying it. Throughout human history, earthquakes have often been remembered because of their destruction. Buildings collapse, roads break apart, bridges fail. Yet some earthquakes become famous for another reason entirely. They alter geography. The June event belongs to that category. Maps drawn before the earthquake and maps drawn afterward may show the same towns, the same mountains, and the same bays, but careful measurements reveal that the physical relationship between land and sea has changed. The shoreline in some locations is no longer where it once stood. This phenomenon has occurred elsewhere around the world. In Alaska during the Great Earthquake of 1964, enormous sections of coastline rose while others subsided. Entire harbours became too shallow for navigation. Former tidal flats emerged permanently above the reach of ordinary waves. In northeastern Japan during the earthquake of 2011, some coastal regions experienced dramatic vertical displacement. The disaster became known primarily for the tsunami that followed, yet the tectonic deformation itself permanently altered parts of the coastline. Southern Mindanao has now joined that list of places where geological forces have rewritten the boundary between land and ocean. The mechanics behind such transformations are rooted in the architecture of subduction zones. The Cotabato Trench forms part of a vast system where oceanic lithosphere bends downward and disappears into the mantle. This process is neither smooth nor continuous. Friction along the boundary causes sections of the plates to lock together. As convergence continues, the overriding plate is dragged and deformed. Imagine pressing one thick board against another while attempting to force them past each other. Friction prevents immediate movement. Pressure builds. The boards bend. Eventually, the resistance fails. One board suddenly jerks. That sudden motion releases the accumulated energy. Although the real Earth is vastly more complicated than two wooden boards, the basic principle remains similar. For years before the earthquake, stress accumulated within the Cotabato system. The rupture released that stress in seconds. The focal mechanism associated with the event strongly indicates compressional motion. Rake values approaching 90 degrees are characteristic of thrust faulting, meaning that vertical displacement dominated the movement. This detail matters because vertical displacement directly influences coastal elevation. Horizontal motion can offset roads and rivers. Vertical motion can create new coastlines. When the hanging wall rises during a thrust earthquake, everything resting upon it rises as well. Beaches, reefs, forests, villages and roads all move together. The process does not distinguish between natural and human landscapes. Everything is carried upward. Reports from affected areas suggest that uplift may have approached several meters or several feet in some locations. Even a rise of roughly 2 meters, equivalent to about 6.5 feet, can produce dramatic consequences in shallow coastal environments. A reef platform submerged beneath only a few feet, or about 1 meter, of water may suddenly emerge completely above sea level. Channels once navigable by small boats may become impassable. Tidal patterns may shift. Habitats may disappear. The exposed coral reefs provide one of the clearest illustrations of these effects. Coral organisms depend on continuous submersion. Their biological systems evolved for life underwater. When uplift suddenly removes that environment, survival becomes difficult or impossible. Reefs that may have taken centuries to develop can be damaged within hours. Scientists examining the affected coastlines are likely to find distinct zones marking the former sea level. Dead coral colonies, stranded marine organisms, and newly exposed limestone surfaces create a visible record of the earthquake's impact. Future studies of these features will help reconstruct the exact pattern of uplift across the region. Long after damaged buildings have been repaired and roads rebuilt, these geological markers may remain. The earthquake also offers an opportunity to observe a process that normally unfolds too slowly for direct human perception. Many mountain ranges around the world owe their existence to repeated episodes of uplift accumulated over millions of years. The forces responsible for creating continents, mountains and plateaus are usually measured in fractions of an inch per year, or fractions of a centimetre per year. Here, however, those forces became visible almost instantly. An entire section of coastline rose within moments. The event compressed geological time into human time. Residents did not need scientific instruments to recognize that something extraordinary had happened. They could simply look toward the sea. Perhaps the most striking aspect of the uplift is its permanence. The newly exposed land is not expected to disappear when aftershocks cease. The shoreline is not expected to return to its former position through natural recovery. Instead, the coastline has entered a new chapter of its geological evolution. Future tides will interact with a different landscape. Future storms will encounter different coastal profiles. Future generations may grow up considering the post-earthquake shoreline normal, unaware that older maps once showed the sea much farther inland. This permanence distinguishes tectonic uplift from temporary coastal changes caused by weather or seasonal cycles. Storms can erode beaches. Tides can expose reefs for a few hours. Ocean currents can reshape sandbars. But tectonic uplift changes the elevation of the land itself. The reference point shifts. Everything afterward must adapt. That adaptation extends beyond geology into ecology. Coastal ecosystems are especially sensitive to elevation. Mangrove forests occupy narrow zones defined by tidal flooding. Seagrass meadows require specific water depths. Coral reefs depend upon precise relationships between sunlight and seawater. When the land rises, those relationships change. Areas previously flooded by every high tide may become dry except during storms. Marine habitats may transition into terrestrial environments. Some species decline, while others expand into newly available territory. The earthquake, therefore, represents not only a geological event, but also an ecological turning point. Scientists monitoring the affected coastline will likely spend years documenting these transitions. Some changes may occur rapidly, others may unfold gradually across decades. Meanwhile, another consequence of the earthquake emerged in reports from Balut Island and neighbouring regions. New sinkholes appeared. Ground deformation associated with large earthquakes often extends beyond the primary fault rupture. Vibrations can destabilize underground cavities, alter groundwater movement, and trigger localized collapses. In regions where soluble rocks such as limestone occur, these effects can be especially pronounced. Water slowly dissolves limestone over thousands of years, creating hidden voids beneath the surface. Most remain stable. A major earthquake can change that stability. The shaking may cause ceilings of underground chambers to collapse. Fractures may enlarge. Existing weaknesses may fail. The result appears at the surface as a sinkhole. Residents observing these features understandably viewed them as among the most unsettling consequences of the earthquake. Unlike exposed reefs, which reveal a process of uplift, sinkholes suggest the opposite. They represent collapse. Together, uplift and subsidence illustrate the complexity of crustal deformation during major earthquakes. The Earth does not move uniformly. Some sections rise, others sink, some fracture, others bend. The landscape that emerges afterward is a patchwork of these responses. This complexity is evident throughout the broader tectonic environment of Mindanao. The island occupies a crossroads between multiple interacting plate systems. Faults intersect, trenches curve, microplates rotate, volcanic arcs mark ancient and ongoing episodes of subduction. The Cotabato Trench forms only one component of this intricate framework, yet it plays an outsized role in shaping southwestern Mindanao. Over millions of years, the trench has influenced the development of mountains, basins, coastlines, and volcanic systems throughout the region. Sediment scraped from the descending plate accumulated into an accretionary wedge. Compression folded and faulted rock layers. Marine sediments were uplifted above sea level. Coral reefs formed, died, and were elevated into terraces. Each geological feature recorded a chapter in the ongoing interaction between tectonic plates. The earthquake of June 2026 became the latest entry in that long geological record. For human observers, the event lasted less than a minute. For the Earth, it represented one moment in a process that has continued for millions of years and will continue for millions more. The same forces that generated this earthquake helped build Mindanao itself. They created the mountains rising inland from the coast. They shaped the deep waters offshore. They influenced the distribution of rivers, valleys, and plains. The earthquake offered a rare glimpse into those forces while they were actively reshaping the landscape. And nowhere was that reshaping more visible than along the newly uplifted shores, where the sea now meets land at a different line than it did before dawn on June 8th. The immediate attention of many communities after the earthquake focused on the sea. That concern was understandable. Large thrust earthquakes occurring beneath the ocean are among the most efficient tsunami generators on Earth. When a section of seafloor rises or falls abruptly, the overlying water column is displaced. That displacement can initiate waves capable of travelling across entire ocean basins. Yet, despite the enormous magnitude of the earthquake, the resulting tsunami remained relatively modest. Wave heights observed in affected areas generally reached around 1 metre, or approximately 3.3 feet. With local variations depending on coastal geometry and bathymetry. Communities reported unusual surges and rapid fluctuations in water level, but the catastrophic inundation that many feared did not occur. This outcome provides important insight into the nature of the rupture. Although significant uplift occurred along portions of the coastline, Much of the earthquake's energy appears to have been concentrated in crustal deformation rather than in generating massive displacement of the water column. The geometry of the fault movement, the depth of the rupture, and the distribution of uplift all influenced the final tsunami size. The earthquake therefore became notable not for a devastating ocean surge, but for something considerably rarer in the public imagination. It changed the shape of the land itself. Across southern Mindanao, the consequences extended far inland from the coast. The shaking reached destructive levels in numerous communities. Buildings suffered structural damage, roads fractured, utility networks experienced interruptions. Schools, government facilities, ports, and commercial establishments faced varying degrees of impact. Strong ground motion spread through cities and municipalities across a wide area. In places nearest the epicentral region, the force of the shaking was severe enough to collapse vulnerable structures outright. Walls cracked, roofs failed, concrete fractured. Older buildings, particularly those not designed to modern seismic standards, proved especially susceptible. The earthquake became a reminder that even regions familiar with seismic activity remain vulnerable when a truly major event occurs. Infrastructure constructed across decades often contains hidden weaknesses. Some structures withstand repeated moderate earthquakes only to fail when confronted with a much larger event. The challenge extends beyond individual buildings. Transportation networks are particularly vulnerable during major earthquakes because they depend on long continuous systems. Roads cross faults. Bridges span rivers and valleys. Ports rely upon stable coastlines. When the earth shifts, every component of those networks can be affected simultaneously. In the aftermath of the June earthquake, engineers faced the task of evaluating not only visible damage but also deformation that might not be immediately apparent. A road can appear intact while its foundation has shifted. A bridge can remain standing while critical structural elements have been weakened. A harbour can survive the shaking yet become less navigable because the seabed has changed elevation. The uplifted coastlines introduced additional complications. Fishing communities found themselves confronting altered coastal environments. Boat launching areas no longer functioned exactly as they had before. Channels and shallow water routes changed configuration. Previously submerged obstacles emerged above the waterline. The relationship between settlements and the sea had been rewritten. For generations, many coastal residents developed an intimate understanding of local shorelines. They knew where reefs lay hidden beneath the water. They knew where currents flowed strongest. They knew which channels remained navigable during low tide. The earthquake instantly rendered portions of that accumulated knowledge obsolete. A reef that once sat safely below the surface might now be exposed. A familiar lagoon could become disconnected from the open sea. A passage routinely used by fishermen might suddenly be too shallow for navigation. Such changes illustrate the extraordinary reach of major tectonic events. The effects extend beyond the moment of shaking. They alter the practical geography through which people live their daily lives. Scientists studying the earthquake have particular interest in the pattern of deformation associated with the rupture. Modern technology provides tools unavailable during many historic earthquakes. Global positioning system stations continuously measure crustal motion with remarkable precision. Satellite radar systems can detect changes in ground elevation across vast regions. Remote sensing platforms allow researchers to compare landscapes before and after major events. These technologies make it possible to reconstruct the earthquake in extraordinary detail. Even before field teams complete their surveys, satellite observations can reveal where the crust moved upward and where it subsided. Networks of geodetic instruments often record sudden jumps in position during major earthquakes, providing direct evidence of crustal displacement. In the case of the Mindanao earthquake, such measurements are expected to help define the geometry of the fault rupture, estimate the amount of slip, and map the distribution of uplift and subsidence throughout the affected region. Every major earthquake becomes a source of scientific information. The June event is no exception. Researchers examining the deformation field will seek answers to several important questions. Exactly where did the largest fault movement occur? How much slip took place during the rupture? Why was the uplift concentrated in certain areas? How does this event compare with previous earthquakes along the Cotabato Trench? The answers will improve understanding not only of this earthquake, but also of future hazards facing southern Philippines. One of the most significant lessons concerns the continued activity of the Cotabato subduction system. For long periods, sections of a subduction zone may appear relatively quiet compared with neighbouring tectonic regions. That apparent quietness can be deceptive. Stress continues accumulating regardless of whether earthquakes are occurring frequently. In some cases, extended periods without major ruptures simply allow larger amounts of strain to build. The history of the Cotabato region demonstrates this principle repeatedly. Major earthquakes, separated by years or decades, are reminders that tectonic systems operate according to geological timescales rather than human expectations. The June rupture revealed that substantial energy remained stored within the region. Its release transformed coastlines, damaged infrastructure, and generated a sequence of aftershocks that continued for days. Yet the broader tectonic process remains ongoing. The plates have not stopped moving. Convergence continues. Stress continues accumulating. The earthquake marked the end of one cycle of strain release and the beginning of another. This reality underscores why geological records are so important. Raised coral terraces, uplifted marine sediments, and ancient shoreline features preserve evidence of prehistoric earthquakes long before written history began. By studying these features, scientists can reconstruct patterns of seismic activity extending thousands of years into the past. The newly uplifted reefs of southern Mindanao may eventually become part of that record. Centuries from now, future geologists might examine them as evidence of the earthquake that struck in 2026. They may measure the elevation of the uplifted coral, determine the age of the event, and compare it with other ancient terraces scattered across the region. In that sense, the earthquake has already become part of the geological archive. The exposed reefs, altered shorelines, and displaced landforms now serve as physical documents written directly into the landscape. Every tide that washes against the new coastline will reinforce that record. Every storm that strikes the uplifted shore will interact with terrain that did not exist in its current form before June. Every map revised to reflect the changed coastline becomes another acknowledgement that the Earth moved. The magnitude 7.8 earthquake demonstrated a truth that is easy to forget during periods of geological calm. Landscapes often appear permanent because human lifetimes are short. Mountains seem immovable. Coastlines seem fixed. Bays and reefs appear timeless. Yet these features exist within an active planet whose surface remains in constant motion. Most of that motion unfolds too slowly to notice. Occasionally, however, the process accelerates. Seconds accomplish what might otherwise require centuries. A coastline rises, a reef emerges, a fault ruptures, an island changes shape. The people of southern Mindanao witnessed precisely such a moment. When daylight revealed the aftermath of the earthquake, the evidence stretched across beaches, reefs, villages and bays. The sea stood farther away, the land stood higher, and along the edge of the Cotabato Trench, one of the most powerful geological forces on Earth, had once again left its unmistakable signature upon the Philippines.